The shore is composed of a glass-like grit, a vast expanse of obsidian sand that drinks the light of a heavy amber sun. Here, the waves of an ancient sea do not merely lap against the coast. They heave with a deliberate, crushing weight governed by a pull of gravity that would make a human frame feel as though it were carved from lead. The sky above is not the familiar cerulean of a terrestrial afternoon, but a deep, saturated gold, thick with the haze of an atmosphere that has clung to this rock for 6 billion years. This sun, a bloated and majestic elder to the one that warms the fields of Earth, hangs low and swollen in the heavens, casting shadows that stretch like long, dark fingers across a landscape of volcanic basalt and weathered stone. 1,400 light-years away, the cradle of humanity is a speck of dust, lost in the glare of a distant spiral arm. To stand here is to occupy a point in space so remote that the very light now reaching the eyes of an observer on Earth began its journey when the Roman Empire was still a fever dream of the future. We are positioned within the dense and glittering starfields of the constellation Cygnus, the Swan, peering into a corner of the Milky Way where the laws of physics have conspired to create a world that is hauntingly, terrifyingly familiar. This is Kepler-452b, a world we have come to call our older cousin, a planet that serves as a silent sentinel guarding the secrets of our own biological destiny. The air here is thick, pressing against the skin with the insistence of a deep sea current. Every breath is a reminder of the sheer scale of this super-Earth, a world 60% larger than our own, possessing a mass that suggests a core of iron and a mantle of churning rock. It is not a place of gentle meadows, but a world of monumental proportions, where the mountains rise with a stubborn defiance against the crushing downward pull, and the valleys are carved by rivers that flow with a slow, viscous grace. The light of the star Kepler-452 is 20% brighter than our own sun, a fierce and unrelenting radiance that has bathed this world in energy for 1.5 billion years longer than the Earth has even existed. There is a profound psychological ache that defines the human condition, a persistent longing to find a mirror in the dark. For as long as we have possessed the capacity to look upward, we have wondered if we are a singular accident or a common occurrence. This world, this calculated reality born from the meticulous observation of distant starlight, is the answer to a question we have been asking since we first huddled around campfires on the African savanna. We do not look at Kepler-452b because it is a convenient destination. We look at it because it represents the possibility of a second home, a place where the grand experiment of life might have already played out its final acts while we were still learning to walk upright. The realization that such a place exists not as a fiction of the silver screen or a dream of a poet, but as a physical entity with a specific address in the cosmos, challenges our fundamental understanding of solitude. We are no longer shouting into an empty canyon, but standing on the edge of a vast and terrifyingly beautiful ocean, knowing that on the other side there are shores just as solid as our own. The distance of 1,400 light-years is a fortress of time and space, a barrier that ensures we may never touch the obsidian sand or feel the warmth of that golden sun upon our faces. Yet, the mere knowledge of its presence changes the weight of our own existence. We find ourselves drawn to this older Earth because it offers a glimpse into a crystal ball. Because its star is older and more luminous, Kepler-452b shows us the twilight of a habitable world. It is a planet that has endured the slow, inevitable expansion of its parent star, surviving through epochs that the Earth has yet to encounter. It is a world that has seen the rise and perhaps the fall of geological eras that make our own history seem like a heartbeat in the dark. The ache we feel when we contemplate this distant cousin is the ache of a child looking at an elder, searching for a sign of what is to come, hoping to find a hint of survival in the face of the encroaching celestial fire. The landscape is silent, save for the low moan of a wind that carries the scent of minerals and ancient chemistry. There are no forests here that we would recognize, no birds to break the golden stillness of the sky. If life exists in this place, it is a life shaped by the tyranny of gravity and the relentless passage of deep time. It is a life that has had 6 billion years to find its footing, to adapt to the heavy pull of the Earth and the fierce glare of the sky. We are outsiders here, ghosts of a younger world, peering through the keyhole of a telescope at a reality that does not require our presence to be magnificent. As we stand upon this imagined shore, we are forced to confront the reality of our own fragility. The Earth is a pale blue dot, a fragile sanctuary in a universe that is indifferent to our survival. Kepler-452b is a reminder that the universe is capable of producing worlds of immense power and longevity, planets that dwarf our own in both scale and history. It is a world that demands we set aside our planetary arrogance and recognize that we are part of a much larger, much older story. The journey to understand this distant mirror is not just a journey of astronomy, it is a journey of the spirit, a search for meaning in a cosmos that is far more crowded and far more ancient than we ever dared to believe. The golden sun sinks lower toward the horizon, turning the obsidian sand into a field of liquid shadows. The light that falls here is a bridge across the void, a signal from a world that was already old when our sun was a mere spark in a collapsing cloud of gas. We are the first generation of our species to know the coordinates of a second home, to have a name for a world that could have been our own. This is the beginning of our journey into the deep, a voyage not of ships and sails, but of mathematics, light, and the unyielding human desire to never be truly alone in the dark. The history of our loneliness is written in the ink of an endless night, a chronicle of a species that spent its infancy believing the heavens were a solid canopy. To the ancient observers, the stars were not suns, nor were they destinations. They were mere pinpricks in a velvet dome, divine sparks or silver nails driven into the ceiling of the world. For thousands of years, the universe was small, intimate, and centered entirely upon the soil beneath our feet. This was a comfortable delusion, a cosmic nursery where the walls were close and the dark held no true depth. There was no room for other worlds in a sky that was merely a backdrop for the dramas of gods and the navigation of sailors. This celestial ceiling began to crack during the 16th century, and the light that spilled through was both revolutionary and dangerous. In the year 1600, in the heart of Rome, the philosopher Giordano Bruno stood before the grim machinery of the Inquisition. He did not merely suggest that the Earth moved around the sun, he committed the ultimate heresy of dreaming of an infinite universe. He looked at the stars and saw not points of light, but countless suns, each perhaps surrounded by its own family of planets, its own theatres of life, and its own civilizations. As the flames of dogma rose in the square of the Campo de' Fiori, licking at his robes and silencing his voice, the idea of a singular, miraculous Earth was being burned away. Bruno died in a state of prophetic certainty, a martyr for a plurality of worlds that the human eye could not yet see. Yet, following the smoke of Bruno's execution, humanity entered a long period of profound cosmic isolation. Even as the telescope revealed the craters of the Moon and the moons of Jupiter, the solar system was increasingly viewed as a lonely clockwork masterpiece. In this era, the universe was reimagined as a barren, mechanical desert, a vast expanse of cold Newtonian physics, where the sun was a unique engine and the planets were its only children. For centuries, we believed we were living in a singular miracle. The stars were recognized as distant suns, yes, but they were seen as sterile furnaces, too far away and too fierce to permit the existence of something as fragile as a world. We were a species adrift in a void of terrifying proportions, convinced that our neighborhood was the only one that had ever been built. The transition from this mechanical isolation to the era of discovery was hampered by the sheer, overwhelming physics of starlight. To search for a planet around a distant star is to attempt a feat of observation that defies the limits of the senses. A star is a screaming engine of nuclear fusion, a searchlight of such staggering brilliance that it obliterates everything in its shadow. Trying to see a planet orbiting such a furnace is like trying to spot a single grain of dust dancing in the beam of a high-powered lighthouse from several miles away. The planet does not shine with its own fire. It merely reflects a pathetic fraction of its parent's glory, a tiny, dark speck lost in a hurricane of photons. In the late 20th century, the search for these hidden worlds turned toward the subtle, invisible tug of gravity. Astronomers began to hunt for a planetary wobble, a rhythmic stagger in the motion of a star caused by the gravitational pull of an unseen companion. This method, known as radial velocity, relied on the stretching and squeezing of light waves, the shifting of colors toward the red or blue ends of the spectrum, as a star moved slightly toward or away from the observer. For decades, this search was a history of failure and frustration. The equipment of the time lacked the precision to detect a movement that was often slower than a human's walking pace, occurring trillions of miles away. The early pioneers of this field were met with a wall of silence. They looked for the telltale shifts in the light of nearby suns, but the data remained flat and lifeless. Every promising signal turned out to be a ghost in the machinery, a flicker of stellar activity, or a simple error in calculation. The scientific community grew cynical, suspecting that perhaps our solar system truly was a freak occurrence, a one-in-a-billion accident of chemistry and orbital mechanics. We remained trapped in a silent, empty canyon, shouting into the dark and hearing only the echo of our own voices. The desert of the cosmos seemed to stretch on forever, devoid of life, devoid of rock, devoid of anything that might mirror the complexity of the Earth. This period of cosmic loneliness was a time of intellectual humility. We had moved from the center of the universe to the periphery of a vast galaxy, yet we remained alone. The infinite worlds of Giordano Bruno remained a beautiful, unproven dream, a philosophical hope that the universe was more than a collection of glowing gas and empty space. We were a species standing on the shore of a dark ocean, unable to see the islands that lay just beyond the horizon, convinced that the water went on forever into a cold and eternal nothingness. The search for a twin, for an older cousin, or even for a simple rock in the dark remained the ultimate challenge of our kind, a desperate attempt to prove that the light of intelligence was not a flickering, solitary candle in an endless, howling gale. The gale of uncertainty was finally stilled in the year 1995, not by a grand revelation from the heavens, but by a subtle, rhythmic shift in the color of a distant sun. Within the quiet, data-driven halls of the Geneva Observatory, two astronomers named Michel Mayor and Didier Queloz were monitoring a star 50 light-years away in the constellation of Pegasus. The star, catalogued as 51 Pegasi, was a sun-like twin to our own, yet its light carried a secret that would dismantle centuries of planetary theory. They observed a periodic wobble, a tiny gravitational tug-of-war that indicated the presence of a massive companion. But the data was nonsensical by the standards of the time. This world, which would become known as 51 Pegasi b, was half the mass of Jupiter, yet it was orbiting its star at a distance so close it completed an entire year in just 4.2 days. This discovery shattered the long-standing planetary arrogance of the scientific community. For generations, the architecture of our own solar system with small, rocky worlds huddled near the warmth and giant, gaseous behemoths relegated to the cold outer reaches was considered the universal blueprint. 51 Pegasi b was a hot Jupiter, a gas giant so scorched by its parent star that its atmosphere was a roiling cauldron of expanded gases, likely reaching temperatures of 1,000 degrees. Its existence was an impossibility. According to the established models of how planets were born, it proved that the universe was far more creative, chaotic, and diverse than our narrow experience had allowed us to believe. The singular miracle of our solar system was suddenly revealed to be just one possible outcome in a cosmic lottery of infinite variety. The impact of this realization was like a tidal wave crashing through the ivory towers of academia. The discovery opened the floodgates for a new era of exploration, transforming the search for exoplanets from a fringe pursuit of dreamers into the most vital frontier of modern science. The question was no longer whether other planets existed, but how many there were and how strange they could become. A gold rush of the intellect began, as observatories across the globe turned their lenses toward the stars with a renewed and desperate hunger. The silence of the mechanical desert was replaced by the frantic noise of discovery, as one world after another began to emerge from the darkness. This shift in the scientific zeitgeist was profound. Astronomers who had once been dismissed for hunting ghosts were now the vanguard of a new age of discovery. They found worlds of diamond, planets where it rained glass sideways in howling winds, and dark globes that absorbed nearly all the light that hit them. Each new find was a hammer blow against the idea of our own uniqueness. We were beginning to see that the galaxy was not a barren void, but a teeming jungle of planetary possibilities. The realization began to take hold that if the universe could create something as bizarre as a hot Jupiter, it must also be capable of creating something as precious as a second Earth. The hunt for a twin, however, required a precision that ground-based telescopes could not achieve. The shimmering of our own atmosphere, the very air that sustains us, acts as a veil that blurs the fine details of distant starlight. To find a rocky world, a planet the size of our own hiding in the habitable zone of a distant sun, we would need to leave the cradle behind. We would need to place a sentinel above the clouds, a machine capable of staring into the deep with an unblinking, mechanical eye. The stage was set for a grand mechanical endeavor to map the heavens, a mission that would require decades of political struggle and engineering genius to realize. The scientific community moved from a state of skeptical isolation to one of focused ambition. The search for 51 Pegasi b had been the crack in the dam. Now, the water was rushing through, carrying with it the hopes of a species that was finally ready to admit it might not be alone. The era of the lone observer with a handheld telescope was over, replaced by the era of the great space-based observatories. We were no longer content to simply wonder if there were other shores. We were preparing to count them, to measure them, and to find the one that mirrored our own. This was the moment humanity transitioned from being a resident of a single world to becoming a student of a galaxy of worlds, a transition that would eventually lead us to a specific set of coordinates in the constellation Cygnus. The arrogance of the past was replaced by a deep, driving curiosity. The realization that the galaxy might be teeming with billions of hidden worlds changed the very nature of our questions. We were no longer asking if planets were out there, but rather where the nearest rocky world lay and whether it possessed the chemistry of life. The search moved from the giant and the violent to the small and the temperate. It was a search for the holy grail of astronomy, a world that was not too hot, not too cold, but just right for the delicate dance of biology. To find it, we would need to build a masterpiece of glass and silicon, a telescope that could watch 100,000 stars at once, waiting for the one moment when a distant world would step into the light. The birth of the Kepler Space Telescope was not a sudden event, but the culmination of a decades-long siege against the impossible. It was conceived as a mechanical monk, a silent and solitary observer cast into the frozen dark of an Earth-trailing orbit. Unlike other telescopes that darted from one celestial object to another, Kepler was designed for a singular, unwavering devotion. It was tasked with staring at a single, unchanging patch of the Milky Way, a field of view containing more than 150,000 stars, and it was commanded never to blink. For years, this machine would remain fixed in its orientation, a silent sentinel watching for the faintest heartbeat of light in the vastness of the Cygnus and Lyra constellations. The method it employed was the transit, a technique that relied on the most subtle of cosmic shadow plays. To understand the transit is to see a star not as a static point of light, but as a roaring lighthouse beam casting its brilliance across the void. If a planet, in its silent trek around its sun, happens to pass directly between that star and the telescope's lens, it will block a minuscule fraction of the starlight. For a few brief hours, the majesty of the star dims by a fraction of a percent. To the instruments of Kepler, this dip in brightness is the signature of a world. It is the only way to detect a dark, rocky sphere that would otherwise be utterly invisible against the glare of nuclear fusion. This vision was the lifework of William Barucki, a man who endured decades of professional skepticism and repeated rejections. Throughout the 1980s and 90s, the scientific establishment viewed his proposal as a fool's errand. The technical requirements were staggering. To detect a planet the size of the Earth, the telescope would need to measure a change in brightness of just 1 part in 10,000. Critics argued that no man-made sensor could ever achieve such precision, especially while hurtling through the vacuum of space. They likened the task to trying to detect a single marble passing in front of a roaring bonfire from several miles away, or spotting a fruit fly crawling across the headlight of a car in a distant city. Baruki, however, was undeterred. He spent years in laboratories and basements, building test beds, and proving that the silicon eyes of a spacecraft could indeed perceive such a microscopic flicker. His persistence was finally rewarded in March of 2009, when the Kepler mission rose from the Florida coast on a pillar of flame, escaping the thick shroud of the Earth's atmosphere. Once it reached its station in the cold silence of space, the mechanical monk began its vigil. The data that began to stream back to Earth was unlike anything humanity had ever seen. The telescope's unwavering gaze began to peel back the veil of the Milky Way, revealing that the darkness between the stars was not empty space, but a crowded gallery of planetary systems. The sheer scale of the census was breathtaking. Kepler did not just find planets, it found that planets were everywhere. It discovered that nearly every star in the sky likely plays host to at least one world. The telescope watched as thousands of these shadows crossed their respective suns, each one a data point in a new map of the galaxy. It found worlds that were scorched, worlds that were frozen, and worlds that defied every category of planetary science. But most importantly, it began to narrow the search for the rocky, temperate worlds that might harbour the chemistry of life. The mechanical monk was not merely counting rocks, it was searching for a home, a mirror, a sister world that had been waiting in the light of Cygnus for billions of years. The data revealed a universe that was far more populated than the most optimistic dreamers had dared to suggest. The statistical reality was inescapable. The Milky Way was a garden of planets. As the years of the mission progressed, the telescope's precision allowed it to see smaller and smaller worlds, moving from the giant gas behemoths to the elusive, rocky spheres that resemble our own. This was the silent triumph of engineering and human will, a machine that could sit in the dark and, by simply watching the light of 100,000 bonfires, find the tiny marbles that made the galaxy a place of infinite possibility. The veil was gone, and in its place was a map of a universe where we were no longer the only inhabitants of a rocky shore. The data from the mechanical monk began to coalesce into a terrifyingly beautiful picture of abundance, a statistical harvest that redefined our understanding of the heavens. It was no longer a question of whether planets were common, but how we could possibly comprehend their sheer number. In the Milky Way alone, the count of worlds reached into the hundreds of billions, an ocean of spheres drifting through the dark. This realization surpassed any previous estimate. There are more planets scattered throughout our galaxy than there are grains of sand on every beach, every desert, and every riverbank of the Earth combined. Each star in the sky is not just a point of light, but a gateway to a system, a centerpiece for a family of worlds that have been spinning in the dark for eons, unseen and uncounted until now. The first fruits of this harvest were the giants. These were the bloated, gaseous monsters that were easy to spot because they cast large, unmistakable shadows. They were the low-hanging fruit of the cosmos planets the size of Jupiter or Neptune that hugged their stars so tightly that they transited every few days. While these discoveries were exciting, they were merely the prelude. They were alien, scorched, and inhospitable, roaring with atmospheric storms that would shred any vessel. The scientific community soon moved past the novelty of these behemoths, turning their collective gaze toward a much more difficult and elusive quarry. The excitement of the spectacular gave way to the grueling, silent search for the holy grail of astronomy, the rocky world. We sought a planet with a solid surface, a place where the chemistry of geology could interact with the chemistry of an atmosphere. More specifically, we sought these worlds within the habitable zone, that narrow, temperate band around a star, where the heat is neither too fierce to boil the oceans away, nor too weak to freeze them into eternal ice. This is the region where water, the universal solvent of life, can exist in its liquid form, pooling in basins and carving through stone. To find such a place, however, required a cold, mathematical precision that pushed the limits of human ingenuity to the breaking point. A rocky planet the size of Earth is a tiny, insignificant thing compared to the vastness of its sun. Its transit does not cause a dramatic dimming. It causes a microscopic flicker, a dip in light so small that it is almost indistinguishable from the natural turbulent noise of the star itself. Stars are not perfect, steady lamps. They pulse, they flare, and they are covered in dark spots that can mimic the signature of a planet. To isolate a terrestrial signal from this cosmic static, astronomers had to employ rigorous algorithms and sift through mountains of digital information. They had to account for the jitter of the telescope, the radiation of deep space, and the inherent instability of the stars themselves. Patience became the primary tool of the planet hunter. To confirm a planet in the habitable zone of a sun-like star, one cannot rely on a single transit. A single dip in light could be a fluke, a passing comet, or a momentary glitch in the silicon sensors. To be certain, the telescope had to witness the event at least 3 times, spaced exactly 1 orbital year apart. For a planet mirroring the Earth's orbit, this meant waiting 3 full years to gather the necessary evidence. The search became a silent exercise in endurance. Scientists spent thousands of hours staring at flickering lines on computer screens, looking for the rhythmic, repeating signature of a world that took its time to circle its sun. There is a specific kind of tension in this work, the knowledge that the data for a second Earth might already be sitting on a hard drive, buried under a mountain of digital noise, waiting for the right person to find it. It is the search for a needle in a haystack, where the needle is made of glass and the haystack is made of light. The stakes were nothing less than our understanding of our place in the universe. We were looking for a sign that the conditions that allowed us to exist were not a cosmic fluke, but a recurring theme in the great symphony of the galaxy. We were looking for a world that had enjoyed the same stability and the same temperate grace that allowed life to flourish on our own. As the years of the mission reached their peak, the noise began to fall away, and the first whispers of rocky worlds started to emerge from the data streams. These were not the scorched giants of the early years, but the small, quiet, and temperate spheres that had been hiding in the glare for billions of years. The census was no longer just a list of numbers. It was becoming a map of potential homes. And among these emerging signals, one particular set of data began to stand out, a world orbiting a sun-like star in the constellation Cygnus, a world that promised to be the most significant discovery in the history of our species. This world, designated as 452b, was about to step out of the shadows and into the light of human consciousness. In the year 2015, a whisper of light deep within the archived data of the Kepler mission solidified into a monumental reality. For years, the signal had been a mere ghost, a repeating dip in the brightness of a star that was nearly indistinguishable from the background chatter of the universe. But as the algorithms refined their focus and the statistical noise was stripped away, the profile of Kepler-452b emerged with undeniable clarity. It was a moment of profound scientific triumph, the culmination of years of patient observation and mathematical rigor. This was not just another gas giant or a scorched rock. It was the first time the instruments of man had detected a world that occupied the same temperate real estate as our own, orbiting a sun that was a near-perfect twin of our celestial parent. The physical anatomy of this world reveals a planet of titanic proportions, a super-Earth that stands 60% larger in diameter than the globe we call home. Its scale suggests a world of immense geological power, where the internal heat of its formation has been trapped for 6 billion years. Beneath its thick, ancient atmosphere lies a rocky crust that has been forged in the crucible of deep time. The world stands as a testament to the endurance of terrestrial architecture, where the mantle likely churns with a slow, heavy rhythm, driving the movement of tectonic plates and fueling the eruptions of massive volcanoes that dwarf the peaks of the Andes or the Himalayas. The surface is a rugged tapestry of basaltic plains and jagged ridges, shaped by the relentless pressure of a gravity that is twice as strong as that of Earth. This world is wrapped in an atmosphere that has matured over 6 billion years. It is a thick, hazy shroud that likely traps the heat of its elder sun, creating a greenhouse effect that has sustained liquid water for eons. The air here is not a thin, fragile veil, but a dense and heavy medium, pressing down upon the landscape with a physical presence that would be felt in every movement of a living creature. The chemistry of this atmosphere is a legacy of its long history, a mixture of gases that have been exhaled by volcanoes and processed by the slow, grinding cycles of planetary evolution. It is an ancient sky, one that has watched its star grow brighter and more golden over 1 billion years longer than the sun of Earth has existed. The discovery of Kepler-452b represents more than a successful mission or a new entry in a planetary catalogue. It is the first time humanity has looked into the cosmic mirror and saw a world that looked back with a haunting familiarity. In its size, its composition, and its distance from its star, it mirrors the essential qualities that make life possible. It stands as a testament to the fact that the architecture of our own world is not unique. For the first time, we have the coordinates of a place that could have hosted the same grand experiment of biology that led to our own existence. It is a mirror that reflects our past, showing us a world that has already survived the epochs we are currently navigating, and it reflects our future, offering a glimpse of what becomes of a rocky world as its sun begins to age. The presence of this planet in the constellation Cygnus challenges the notion of our own isolation. It is a physical reality that occupies a specific point in space and time, a world where the sun rises and sets over a horizon of stone and sea. The familiarity of its features, its rocky surface, its potential for water, its sun-like parent creates a bridge across the 1,400 light-years of empty space. We no longer have to wonder if such worlds exist. We now have the data to prove it. The information has transformed a distant speck of light into a place with a geography, a climate, and a history. This scientific triumph is a milestone in the biography of our species. We have moved from the era of speculation to the era of precision, where the existence of an older Earth is a matter of fact. The haunting familiarity of Kepler-452b serves as a beacon, drawing our curiosity toward the possibilities of what a world can become when it is given 6 billion years of stability. It is a world that has had more time than our own to develop, to change, and to perhaps foster the rise of something complex. As we peer into this distant mirror, we are looking at the potential for a history that is longer and deeper than our own, a narrative of a world that was already old when the first life forms began to stir in the oceans of the Earth. The gravity of the discovery is matched only by the physical gravity of the planet itself. To think of Kepler-452b is to think of a world where everything is more substantial, more enduring, and more ancient. It is a world that has stood the test of cosmic time, maintaining its atmosphere and its temperate climate, while countless other worlds have been stripped bare or frozen solid. It is the first true glimpse of a world that could be called a second home, a place where the light of a familiar sun shines on a landscape of stone and water, waiting for its story to be told. The weight of existence on Kepler-452b is a constant, unrelenting force. With a surface gravity twice as powerful as that of the Earth, every atom of a living organism is pulled toward the core with a double intensity. In this environment, the very architecture of life is dictated by the crushing demand of the vertical. There are no tall, slender stalks or fragile, spindly limbs here. Instead, evolution favors the squat, the broad, and the reinforced. The life forms that have emerged from this crushing environment are shorter, sturdier, and built to withstand a relentless downward pressure that would shatter the bones of any terrestrial visitor. Their skeletal structures, whether internal or external, are likely composed of dense, mineralized lattices, thick enough to prevent the collapse of their own mass under the weight of the air and the pull of the ground. Musculature on such a world is not merely for movement, but for the fundamental preservation of form. Every step is a deliberate triumph over the planetary pull. The circulatory systems of these beings are marvels of biological engineering, equipped with powerful, multi-chambered hearts capable of pumping fluids against a resistance that would leave a human heart stuttering and still. The height of life is restricted by the physics of the planet. The canopy of a forest on this world would sit low to the ground, a carpet of dense, sturdy vegetation that spreads horizontally rather than reaching for the sky. The leaves are thick and leathery, designed to absorb the intense radiation of an elder sun while resisting the physical stress of a heavy, pressurized atmosphere. This biology of strength is a direct response to the star that dominates the sky. Kepler-452 is a glimpse into the future of our own solar system, a G-type star that has reached its golden years. It is 1.5 billion years older than our Sun, a temporal distance that has allowed it to swell in both size and luminosity. It shines 20% brighter than the star that warms our own fields, casting a fierce, golden radiance that has baked the surface of its planet for 6 billion years. This increased brightness creates a relentless thermal pressure, pushing the boundaries of the habitable zone further and further away from the stellar core. The habitable zone is not a static sanctuary, but a shifting, precarious boundary defined by the interplay of geology, chemistry, and the passage of deep time. For a world to remain temperate over such a vast span of history, it must possess a sophisticated internal thermostat. On Kepler-452b, the carbon silicates cycle the process by which carbon dioxide is scrubbed from the atmosphere by rain and buried by plate tectonics must operate with a terrifying efficiency. As the star grows brighter and more aggressive with age, the planet must shed its greenhouse gases at a rate that offsets the increasing heat. It is a delicate dance on the edge of a knife. Too much carbon in the atmosphere, and the world becomes a hothouse like Venus. Too little, and it loses its protective blanket and freezes into a barren wasteland. This balance is caught in the relentless gears of deep time. 6 billion years is a duration almost impossible for the human mind to scale. It is long enough for entire mountain ranges to rise and be ground into dust several times over. It is long enough for life to have transitioned from the simplest chemical replicators to complex, sentient architects of their own destiny. The geology of the planet is a slow-motion engine, fueled by the radioactive decay of elements deep within its mantle, providing the energy needed to recycle the crust and keep the atmosphere in a state of breathable equilibrium. Yet, as the star continues to age and brighten, the engine of the planet must work harder to maintain the cooling required for liquid water to exist. The habitable zone on this world is a testament to the resilience of terrestrial planets. It shows that a world can withstand the slow, terminal brightening of its star if its geological heart remains strong. However, this stability is not eternal. There comes a point in the life of every star when its heat overcomes the defenses of its planets, when the oceans begin to boil away into the sky, and the chemistry of life can no longer find a foothold. On Kepler-452b, we see a world that has held onto its habitability longer than the Earth has even existed. It is a world of survivors, a place where life has had to be stronger, tougher, and more resourceful than anything we have ever known. The light that bathes the obsidian sands is heavy with the weight of these eons. It is a brilliant, unforgiving glow that demands adaptation. The creatures of this world are the masters of gravity and the stewards of a world in its long afternoon. They live in the shadow of a sun that is slowly becoming a tyrant, navigating a landscape where every breath and every movement is a testament to the endurance of the biological spirit. As we observe this older cousin from our distant vantage point, we are not just looking at a planet, we are looking at the ultimate endurance test of a living world, a preview of the struggles that our own biosphere will one day face, as our sun follows the same inevitable path toward its swollen, luminous end. This older sun and its heavy planet exist in a state of magnificent, precarious grace. The chemistry of the atmosphere and the geology of the crust are locked in a struggle against the entropy of the star. It is a world that has matured, a world that has reached a level of complexity that only time can provide. The heavy gravity and the bright sky are the defining characteristics of a world that has moved past its youth and is now navigating the complexities of middle age in a galaxy that is indifferent to the survival of its children. In the face of such forces, the existence of a habitable world is a triumph of balance over chaos, a rare and beautiful alignment of physical laws that allows a rock in the dark to become a home. The revelation of this older Earth is immediately tempered by a cold and mathematical cruelty. The distance between our world and this elder cousin is 1,400 light-years, a number that represents a fortress of space and time so vast that it defies the traditional metrics of human exploration. To speak of light-years is to speak of the speed of light itself, the absolute speed limit of the universe, traveling at nearly 300,000 kilometers every single second. A photon leaving the surface of the star Kepler-452 must journey through the freezing vacuum for 14 centuries before it finally strikes the lens of a telescope on Earth. When we look at this world, we are not seeing it as it exists today. We are peering at a ghost from the past, observing the planet as it was when the Roman Empire was collapsing and the Middle Ages were only just beginning to stir. The tyranny of this distance becomes even more crushing when measured against the limits of human technology. Consider the fastest machine ever forged by our species, the New Horizons spacecraft, which hurtled toward the outer reaches of our solar system at speeds exceeding 58,000 kilometers per hour. This vessel, a triumph of engineering that crossed the orbit of the Moon in a few hours, is essentially stationary when compared to the interstellar gulf. If we were to launch such a probe toward the constellation Cygnus today, the journey to Kepler-452b would span 26 million years. This is a duration that exceeds the entire history of the human lineage. 26 million years ago, the ancestors of humanity were small, primitive primates navigating the dense jungles of an unrecognizable Earth. If a ship were launched now, by the time it arrived at its destination, the very species that built it would have either evolved into something entirely different or vanished forever into the silent layers of the fossil record. This is the profound isolation of the human condition. We have reached a point in our development where we can identify our neighbors, map their atmospheres, and calculate their gravity, yet we remain marooned on our small island of light. We stand on the shore of our own world, looking out across a cosmic ocean that we can see with exquisite detail but can never touch. The stars are no longer just points of light. They are destinations that are physically closed to us by the laws of physics. The sheer scale of the vacuum between us and the older Earth acts as a biological barrier, ensuring that the two worlds remain forever separated by the gulf of time. We are a species that has conquered the land, the sea, and the air of our own planet, only to find ourselves stopped at the shoreline of the interstellar void. Our current technology, for all its brilliance, is revealed as a collection of fragile toys when placed against the backdrop of the Milky Way. Our rockets are chemical firecrackers, our probes are tiny metal sparks in a howling gale of radiation and darkness. The energy required to move a physical object across 1,400 light-years in a human lifetime is so immense that it challenges our understanding of power and propulsion. To bridge such a gap would require the harnessing of stars, the manipulation of the fabric of space-time, or the discovery of physics that we have not yet even begun to dream of. Until that day, we are left with the silence of the vacuum and the realization that the universe is partitioned into lonely cells of habitability, each separated by distances that preclude any hope of physical contact. This vastness emphasizes the scale of the cosmic ocean that surrounds us. We live in a galaxy that is 100,000 light-years across, a swirling disk of 400 billion stars, and we are tucked away in a quiet corner of a minor spiral arm. The search for Kepler-452b has taught us that the galaxy is full of potential homes, but the distance has taught us that we are effectively alone. Every discovery of a new exoplanet is a bittersweet victory. It is the finding of a new island in a sea so wide that no boat can ever cross it. We are the inhabitants of a single grain of sand, looking through a magnifying glass at another grain of sand on the other side of the world. The psychological weight of this reality is the defining struggle of the modern era. We are the first generation of humans to know the exact address of a second home while being physically unable to ever set foot on its soil. This knowledge creates a unique form of cosmic melancholy, the realization that we are part of a larger community of worlds that we can never truly join. We are observers of a grand theatre, watching the play from the very last row of the gallery, unable to participate in the drama. The distance is not just a physical measurement. It is a fundamental part of the universe's design, a mechanism that preserves the isolation of life and keeps the secrets of each world locked away behind the speed of light. As we look toward the star fields of Cygnus, we must accept that our relationship with the older Earth will always be one of light and information, never of physical presence. We will continue to build better eyes to see it, better ears to listen for it, and better minds to understand it. But the obsidian sands of that world will remain untrodden by human feet. The void is the ultimate master of our destiny, a silent and eternal expanse that reminds us, with every passing second, that while we have found a mirror in the dark, the glass is too thick to ever break. We are left to wonder, to calculate, and to mourn the beautiful, unreachable reality of a neighbor that lives and breathes 1400 years in our past. The silence of the cosmos is not merely an absence of noise, it is a profound and heavy weight that presses against the collective consciousness of our species. When we look toward the coordinates of Kepler-452b, we are confronted by the most haunting question in all of science, the Fermi paradox. This world has enjoyed 6 billion years of geological stability, a span of time that exceeds the entire history of the Earth by 1.5 billion years. On our own world, life transitioned from simple chemical replicators to a spacefaring civilization in roughly 4.5 billion years. If a similar spark of biology ignited on the obsidian shores of our older cousin, that civilization would have had a head start of 1,500 million years. They should not only be more advanced than us, they should have reshaped their entire star system, or even the galaxy itself, into a beacon of intelligence. Yet, as we turn our most sensitive radio telescopes toward that distant golden sun, we hear nothing. There are no rhythmic pulses of information, no leakage of television broadcasts from an alien metropolis, no megastructures casting shadows across the star. The silence from the direction of Cygnus is absolute. This lack of evidence leads us to the concept of the Great Filter, a theoretical wall that prevents life from progressing beyond a certain point. It suggests that perhaps the flame of intelligence is not a steady light, but a flickering candle that is almost always extinguished before it can reach across the void. The older a planet becomes, the more opportunities it has to encounter a catastrophe that ends the biological narrative. The Great Filter may be a product of the very intelligence it seeks to preserve. As a species masters the fundamental forces of nature, the atom, the genome, the climate, it creates tools of its own destruction that outpace its wisdom. We must consider the possibility that on a world 6 billion years old, the history of civilization is not a linear climb toward the stars, but a series of rises and falls ending in a final, terminal collapse. Perhaps the atmosphere of Kepler-452b was once filled with the signals of a thriving culture, only to be silenced by the hubris of a species that mastered the fire of the sun before it mastered the impulses of its own heart. A runaway greenhouse effect, a global conflict fought with weapons of subatomic precision, or a biological error that unraveled the very fabric of their biosphere. Any of these could have turned a living world into a silent tomb long before our own sun was even born. This silence is suffocating because it suggests that the window for a civilization to communicate across the stars is terrifyingly narrow. It turns our search for siblings into a somber meditation on the fragility of everything we have built. If a world with a billion-year head start could not find a way to make its presence known, what hope do we have of surviving our own technological adolescence? The Great Filter may lie ahead of us, a looming shadow that has already claimed every other civilization that dared to dream of the infinite. In this view, Kepler-452b is not a mirror of our potential, but a graveyard of our ambitions, a place where the music of a world was played to completion and then faded into the eternal background radiation of the universe. The silence also forces us to consider the many ways a world can die through natural means before its star ever reaches the end of its life. Over 6 billion years, a planet faces a gauntlet of cosmic threats. It must survive the impact of rogue asteroids, the lethal radiation of nearby supernovae, and the slow, grinding changes in its own internal geology. If the tectonic engine of a world cools too quickly, its magnetic shield fails, allowing the solar wind to strip away the atmosphere and boil the oceans into space. A planet can be a paradise for 5 billion years, only to become a scorched husk in the final billion. The history of Kepler-452b may be a story of a world that simply ran out of time, a biosphere that was slowly choked to death by the increasing luminosity of its aging sun. This realization transforms the older Earth from a beacon of hope into a cautionary tale. We are shouting into a canyon that may have no bottom and no inhabitant left to hear us. The loneliness of the cosmic neighborhood is not just a matter of distance, but of timing. To communicate with another civilization, we must not only occupy the same galaxy, but we must also exist at the exact same moment in the vast timeline of the universe. We are like two fireflies blinking in a dark forest, separated by miles of trees and hours of time, the light of one failing long before the other is even born. The philosophical weight of this realization is immense. We are the first generation of humans to know the exact address of a second home, yet we must accept that the home may be empty. We find ourselves looking at a world that has already lived through its golden age, a world that may have seen its last sunrise over a living ocean millions of years ago. The Great Silence is the universe's way of reminding us that life is a rare and fleeting phenomenon, a spark of complexity in a universe that is trending toward cold, dark entropy. As we listen to the static from Cygnus, we are not just searching for aliens, we are searching for a reason to believe that our own story does not have to end in the same quiet, lonely darkness. We are looking for a way to break the filter, to be the one species that finally finds a way to endure when the world beneath its feet begins to grow old and tired. The golden sun, Kepler-452, is no longer the gentle provider of life it may have been in the deep past. It has entered its long, aggressive afternoon, a phase of stellar evolution where the hydrogen at its core is being consumed at an accelerating rate. As the core contracts under its own weight, the temperature rises, forcing the outer layers of the star to push outward with an increasing, fierce luminosity. This elder sun now shines with a brilliance 20% greater than the star that warms the Earth, and this extra energy has triggered a catastrophic transformation on the world that orbits it. We are witnessing the final, agonizing stages of a runaway greenhouse effect, a planetary fever from which there is no recovery. The oceans that once defined the geography of this super-Earth are gone. They did not vanish in a single moment of fire, but were bled away over the course of millions of years. As the star brightened, the surface temperature of the planet climbed, causing the rate of evaporation to skyrocket. The atmosphere became saturated with water vapor, a gas that is a far more potent trap for heat than carbon dioxide. This created a lethal feedback loop. The more the oceans boiled, the more the atmosphere thickened with steam, and the more the heat was held against the surface. The temperature surged past the boiling point of water, turning the seas into a global shroud of white mist that blocked the view of the stars, but allowed the heat of the sun to pour in. In the upper reaches of this humid atmosphere, a process called photolysis began to dismantle the very foundations of the world's water. The intense ultraviolet radiation from the elder sun struck the water molecules, tearing the oxygen from the hydrogen. The hydrogen, being the lightest element in the universe, was too energetic for even the planet's double gravity to restrain. It leaked upward, escaping the atmosphere and drifting away into the interstellar void, lost forever to the vacuum. Without hydrogen to recombine into water, the oceans could never return. The oxygen stayed behind, reacting with the minerals in the crust to turn the world into a rusted, oxidized wasteland. This is the crystal ball through which we must view the inevitable future of our own Earth. In approximately 1 billion years, our Sun will undergo the same physical transition. It will grow more luminous, its heat will swell, and the delicate thermal balance that allows life to flourish will be shattered. The Earth will experience the same terminal rise in temperature. The green canopies of the rainforests will wither and ignite. The ice caps will melt into rising seas that will eventually begin to steam, and the very air will become a suffocating blanket of moisture. We are looking at a preview of our own biosphere's execution. The transition from a living, breathing world into a tomb of sand and steam is a fundamental law of stellar proximity. The landscape of Kepler-452b is now a scorched and dry husk. Where there were once obsidian shores and crashing waves, there are now only vast, cracked plains of salt and sun-bleached basalt. The mountains, once capped with snow or covered in hardy, low-slung vegetation, are now jagged skeletons of stone, scoured by a wind that carries no moisture and no life. The sky is a pale, metallic white, a thick haze of dust and sulphurous gases that reflects the bloated, golden sun. There is no sound here but the low, dry moan of the atmosphere moving over a dead geography. The internal geological engine of the planet may still be churning, but it no longer has a surface chemistry to interact with. The carbon cycle has stopped. The biology is a memory. This terminal state is the fate of any rocky world that stays too long in the embrace of its parent star. As the habitable zone moves outward, the planets that were once in the sweet spot of liquid water are left behind in the heat. We see a world that has been stripped of its dignity, a planet that was once a twin to our own but is now a warning. The ferocity of the elder sun has scoured the surface clean of its history, leaving only the most resilient minerals to bake in the eternal glare. It is a world of monumental silence, a place where the steam has long since dissipated into space, leaving behind a desert that spans the entire globe. The realization that this world is a graveyard of a potential civilization is a heavy burden. If life ever walked upon these obsidian sands, its traces have been erased by the relentless thermal scouring of the star. The cities, the monuments, the very fossils of that world have likely been ground into dust and baked into the crust. We are looking at the end of a story that lasted 6 billion years, a narrative of survival that was eventually defeated by the simple, inevitable physics of stellar aging. The older Earth is a mirror not just of our biology, but of our mortality. It shows us that even the most stable and enduring worlds are ultimately ephemeral, caught in a cosmic cycle of birth, maturity, and heat death. As we peer through our telescopes at this distant, scorched rock, we are forced to confront the limits of planetary life. A world can be a sanctuary for eons, but it cannot escape the evolution of its star. The tomb of sand and steam that is Kepler-452b is a testament to the fact that habitability is a fleeting gift. We live in the brief, golden morning of our own world, a time of liquid water and temperate air, but the afternoon is coming. The older cousin stands as a silent witness to the end of all things, a world that has already crossed the threshold into the long, hot, dark, leaving us to wonder how we will spend the remaining billion years of our own world's light. The migration of civilizations is not a choice born of curiosity, but a theoretical necessity dictated by the thermodynamics of a warming sun. To remain on a world like Kepler-452b as its star swells is to accept a slow dissolution into the steam and salt of a dying biosphere. Thus, the physics of the interstellar arc becomes the final blueprint for any species that wishes to outlive its cradle. These vessels are not mere ships, but enclosed ecosystems, monumental cylinders of iron and magnetism hurtling through the vacuum at a fraction of the speed of light. Within these hulls, the very definition of humanity must undergo a radical transformation. The fragility of the biological frame, its constant need for oxygen, for liquid water, and for the specific gravitational pull of a planetary mass, is a liability in the deep dark of the interstellar gulf. The preservation of human consciousness in light offers the only viable bridge across the 1400 light-years of silence. In this transition, the biological mind is translated into a stream of structured photons or a complex lattice of silicon memory allowing the essence of a species to bypass the limitations of meat and bone. In such a state, a journey that spans 26 million years is not a sentence of boredom and decay, but a momentary pause in a digital stream. The Ark becomes a vessel of pure information, a spark of intelligence drifting through the void until it encounters a younger, cooler sun with a world that has yet to begin its terminal warming. This migration is the ultimate act of defiance against the entropy of a single star, a way for the flame of consciousness to leap from one guttering candle to another. We must look forward into the deep future, beyond the life cycles of individual stars, to the eventual end of the era of starlight itself. We currently inhabit the stelliferous era, a brief and glorious epoch in the history of the cosmos, where the darkness is punctuated by the brilliant fire of nuclear fusion. But this era is a fleeting anomaly in the true timeline of the universe. As the hundreds of billions of years stretch into trillions, the vast clouds of hydrogen and helium that birth new suns will be exhausted. One by one, the great lights of the Milky Way and every other galaxy will flicker and fail. The blue giants will vanish first in spectacular explosions, followed by the steady, yellow stars like our own Sun and its older cousin in Cygnus. Eventually, even the small, stubborn red dwarfs, the longest-lived furnaces in the universe, will exhaust their fuel and fade into the cold. In this encroaching twilight, the memory of Earth-like planets will fade into the background noise of a cooling universe. The obsidian sands, the golden skies, and the crashing waves of liquid water will be lost to the increasing disorder of entropy. The universe will transition into the degenerate age, a dark expanse populated only by the cold cinders of white dwarfs, the dense husks of neutron stars, and the inescapable maws of black holes. In this vast, eternal night, the concept of a habitable zone or a temperate world will be a myth from a forgotten age of light. The planetary story, which seems so monumental to us now, is merely a single, bright paragraph in a book of infinite, empty pages. Yet, the rarity and fragility of these worlds do not diminish their significance. They elevate them to the status of cosmic masterpieces. The beauty of the ephemeral lies in its refusal to last. The fact that a world like Kepler-452b exists for only 6 or 7 billion years in a universe that will endure for trillions of trillions makes every moment of its biological complexity a miracle of timing. We are precious precisely because we are temporary. Our current existence on this small, blue island and our ability to perceive its older cousin across the void is a defiance of the encroaching dark. We are a brief and beautiful song sung in a canyon that is slowly falling silent, and the melody is made more poignant by the knowledge that it must eventually end. The fragility of a habitable world is the very thing that gives our search meaning. If every rock in the dark were a paradise, the Earth would be a commodity. Because the Earth is a rare alignment of chemistry and heat, it is a treasure. The older Earth in Cygnus serves as a reminder that we are living through the most vibrant chapter of the cosmic narrative. We are the witnesses who got to see the stars while they were still bright, the ones who lived in the era when the universe was still capable of producing the warmth of a sun and the solid ground of a planet. To be alive now is to hold a winning ticket in a lottery of impossible proportions, occupying a thin slice of time where the conditions for thought and observation are perfectly met. The final flickers of the last stars will mark the ultimate conclusion to the planetary story. These last embers, glowing with a deep and dying red, will provide the final scraps of warmth for whatever remnants of consciousness have managed to endure. When those stars finally go dark, the era of worlds will be over. The story of the obsidian sand, the golden sun, and the search for a mirror in the dark will reach its final page. But until that moment arrives, the existence of these fragile, beautiful mirrors in the dark provides us with a purpose. We are the universe experiencing itself, a collection of atoms that has gained the ability to look back at its own origin and mourn its own inevitable end. The knowledge of our older cousin does not make us feel small, it makes us feel significant, for we are the only ones who can tell the story of the light before the night becomes eternal. The traveller stands once more upon that shore of glass-like grit, the obsidian sand shimmering beneath a sun that has grown heavy and gold with the burden of 6 billion years. The waves heave with a deliberate, rhythmic weight, and the thick atmosphere presses against a form that does not truly displace the air. This traveller possesses no heartbeat, no lungs to draw in the pressurized nitrogen, and no skin to feel the heat of the elder star. This figure is a phantom, a ghost of human curiosity and scientific imagination that has travelled 1,400 light-years across the void to occupy a world that our bodies can never reach. It is the composite shadow of every astronomer who has ever peered through a lens, every engineer who has calculated an orbital trajectory, and every dreamer who has looked at the constellation Cygnus and refused to believe in a silent universe. This spectral presence is the bridge between the data streaming into our silicon sensors and the physical reality of a rocky world. We have sent our minds where our machines cannot yet go, using the cold precision of mathematics to reconstruct a landscape of basalt and steam. The traveller is the embodiment of the human spirit's refusal to be contained by the limitations of the cradle. We are a species that has learned to project its consciousness across the interstellar gulf, turning a microscopic dip in starlight into a vivid, tangible shore. In this sense, the traveller on the obsidian beach is as real as the light that hit the telescope's mirror. They are the final result of the universe's long process of becoming aware of its own vastness. We are the universe experiencing itself, a collection of atoms born in the hearts of dying stars that has regained the ability to look back at the furnaces of its origin. This search for siblings across a terrifyingly vast ocean is not a luxury of a wealthy civilization, but a fundamental drive of our biological and intellectual nature. We seek Kepler-452b because it represents the first true mirror we have found in the dark. It is a mirror that reflects our deepest desire to survive the inevitable death of our own sun, showing us that a rocky world can endure for eons beyond the current age of the Earth. It tells us that the conditions for life are not a singular accident, but a recurring theme in the grand symphony of the galaxy. The legacy of this older cousin is the gift of a specific address for our hopes. Before its discovery, the idea of an Earth-like world was a statistical probability, a beautiful but abstract theory. Now, it is a coordinate in the sky, a physical place with a gravity we can calculate and a sun we can name. This knowledge changes the destiny of the human spirit. It provides a destination for the imagination and a benchmark for our own survival. It forces us to confront the reality that we are part of a much larger, much older story, one that began long before our sun, coalesced from a cloud of gas, and will continue long after our world has become a scorched and silent husk. As the phantom traveller looks back toward the distant, invisible speck of the solar system, the realization takes hold that the search for a twin is also a search for a way to break our own isolation. We are shouting into a canyon that spans 1,400 light-years, not because we expect an immediate answer, but because the act of shouting is what defines us as a sentient species. We are the ones who look for the light in the dark, who count the flickers of distant bonfires, and who refuse to accept that the silence of the cosmos is the final word. Kepler-452b is the proof that the universe is capable of making a home more than once, and that the architecture of our existence is written into the very laws of physics. The beauty of this distant world lies in its unreachable nature. It remains a sanctuary of the mind, a place where the oceans might still be liquid, or where the ruins of a billion-year-old civilization might lie buried beneath the obsidian sand. It is a world of infinite possibilities precisely because we cannot touch it. The distance preserves the mystery, allowing it to remain a beacon for our curiosity and a mirror for our fears. It reminds us that while we are small, our reach is infinite. We have mapped a world that we will never walk upon, and in doing so, we have expanded the boundaries of what it means to be human. The screen of human history is currently bright with the light of discovery, but the shadows are long. We live in a brief window of time where the stars are visible and the planets are within our intellectual grasp. The older Earth in Cygnus is a reminder to cherish the fragile, temperate grace of our own world while we still possess it. It is a call to wisdom, a plea for a species in its technological youth to look at an elder and learn the lessons of deep time and stellar evolution. The mirror does not just show us a second home, it shows us the responsibility we have to the only home we currently inhabit. The narrative of our older cousin concludes not with a certainty, but with a haunting and symmetrical thought. The golden sun of Kepler-452 sinks toward the horizon of the obsidian shore, casting its long, distorted shadows across the volcanic plains. In that same moment, 1,000 light-years away, our own sun is a tiny, unremarkable yellow dot in the sky of another world. The possibility remains that somewhere, on a rocky shore we will never touch, beneath a sky we will never breathe, someone or something is standing in the glow of their own sunset. They are looking back at our star, a flickering spark in their own constellation of the Seeker, standing on their own shore of glass and stone, and wondering with the same profound and aching hunger if they are truly alone in the deep. The silence of the universe is not an answer, but an invitation to keep looking, to keep dreaming, and to keep reaching across the light years until the dark is no longer a barrier, but a bridge.